Assalamualaikum warahmatullahi wabarakatuh. Welcome to a lecture video of week 6. So today we're going to discuss about, basically it's the third part of our discussion on BJT, on bipolar junction transistor. And what we're going to do today is basically we'll discuss about biasing. So biasing is basically it is the discussion on how do we set up the current inside the base to operate the transistor in its linear operating mode. Okay, so a quick recap on what we have seen in week 1. We have basically looked into the structure of the PNP junction in terms of its semiconductor structure, and then in week 2 we have looked into several application using BJT. So this week what we're going to look at is basically is also an application. So we are going to concentrate more on the biasing part, which is basically the way that we could do to control the current in the base in order to produce an output across the collector emitter junction. So in order to review, we have to review a bit the thing that we have seen in first, especially in first and second week. So in terms of approximation, basically a PNP junction or BJT can be simplified into an equivalent electrical circuit, right? So in summary, we will say that the collector side, so here we have our BJT, here we have our base, collector and emitter. So the collector side, it function as act as basically like a current source. So it can be modeled as a current source that pumps up a current that is proportional to IB. Okay, so we are considering that across the BE junction, the PN junction of BE, we have that 0.7 volt that switch on the transistor. Therefore, in left part is basically is the equivalent circuit of our base loop, and the right part what we have is basically an equivalent circuit of this collector emitter loop. Okay, so in collector what happens is basically it acts as what we could call as current source, where it pumps up current, pumps down current from C to emitter, collector to emitter, with a current that is proportional to the base current, with a coefficient of proportionality of B, which is the what we call as current gain. Okay, so current gain, as you remember, the current gain beta is the relation between I current in collector and current in the base. So the step that we need to do in order to deduce basically the output of collector emitter voltage. So in a transistor, basically what we would like to have is we are controlling the base through a certain voltage and a certain probably certain resistor. We'll see later there's a different method of controlling this base current. So for example, here we have 10 volts also supplied to the base loop and 10 volt to the collector loop. So in the base loop, basically we could call it as input, where you have a certain input into the base to switch it on, and in output basically we would have the VCE, the voltage across collector emitter. So in application, for example, in an inverter, in the power electronics of electrical machine of a motor, basically it is this VCE, the voltage across collector and emitter, that is used to supply supply power to the load. Okay, so this is this base part is the control part. The input we are controlling on or off, switching on, switching off, and VCE is the voltage that we are supplying to the load later. So the load is basically your application. It could be an electrical machine, a motor, or it could be any other application as well. So the steps, as you know, in order to get to calculate the VCE, what you need to do first is calculate the base current IB from the base loop. So the base loop here is basically 10 volts. Also here we put only one voltage, because this voltage is basically the same for VBB and VCC. You can connect it together like this. So from the this is the base loop, I'm sorry. And then from the base loop you calculate IB. So you know, you do KVL, you calculate you will manage to calculate IB, and then from IB you calculate IC by using the coefficient of current gain, right? So the current gain will be given in datasheet depending on the value of IB you have. As you might remember, in terms of the curve characteristic of a transistor IC versus VCE. So IC will have a different curve depending on different beta depending on IB. So you'll get beta in the datasheet multiplied by IB, you'll get IC. And then at the end, you will deduce VCE once you have IC. Basically, IC is the current that's circulating in the collector loop. So you can calculate VCE by writing the KVL inside the collector loop. Okay. So in summary, the equation that you need to look at is this equation. So calculating IB is equal to VBB minus VBE over RB. IC is beta multiplied by IB. So VCE is VCC minus IC RC. Here we will have a look at a real data sheet in order to do a certain application. It would be better to have a look at the real data sheet that you will probably encounter when you try to design a circuit later and try to integrate a transistor into your design. So let's have a look at how do we read a data sheet and what are the most important components or importance parameters that we have to look at inside a datasheet of a transistor. So there are before we start, there are two types of transistors. When you're choosing transistors, basically there are what we call a small signal transistor and power transistor. So in a small signal transistor, it is transistor that use just for small electronic circuits, where in total it dissipates power less than 1 watt. So it's a very small transistor that could manage in the output basically a level of voltage and current that produce in total power that is less than 1 watt. And then we have a group of transistor that we call as power transistor, where the transistor could dissipate a power that is larger than 1 watt. So basically in this kind of transistors or switches, we call it sometimes switches, are used in power electronics. It means it used in controlling electrical machine and motors, supplying turning on and turning off basically power to control an electrical machine and motors. Okay, so this kind of transistor in power transistor, basically the power comes from the circulation of current that could be very high. So the current that circulate between your in IB, of course IB will always be small, but the current that circulate in your collector and emitter in the loop, collector loop, is very high, because and the VCE, voltage across the collector and emitter, that is supplied to the application, is also very high. So there is a power transistor. So in the data sheet, so today we're going to look at an example. It's a data sheet of the family of a transistor that is called 2N3904. So 2N3904 is basically is an NPN, general purpose amplifier. So it is a small signal transistor where it has a quite so the total power that it can deliver is less than 1 watt. So on a data sheet, what we are going to look at is always at the maximum rating. So what we want to pay attention to is the maximum rating that we could find in the data sheet, because it is basically the limit that we cannot go beyond, right? So it's a limit not to go beyond, right? So in designing a system, for example, let's say you would have a maximum current required by your load or your system at, for example, at 0.1 amp. You need to check, is that also the maximum current? Is the maximum current of your transistor larger than the maximum current of your application? Okay, let's take a look at an example of a datasheet, and let's extract out the most important parameters that we could find in a datasheet of a transistor. So the first one is what we call as breakdown ratings voltage. So first, if you look at the datasheet, of course, there's the name of manufacturer, then the code of the transistor, and then it's written a bit of features where it says, for example, used in dynamic range extend to 100 milliamps. So basically this is 0.1 amps maximum current transistor, and then there's also the switching frequency. So it is basically related to the speed in which you can switch on and switch off the transistor. So the next thing that we would like to look at is basically the part where it's written absolute maximum rating. Here in the first part, what we have is basically what we call as breakdown ratings, or breakdown rating, as you know, is basically is the rating of different value. Basically, here are the voltages. The voltage in reverse that would break your PNP junction. Okay, so if you put a voltage across that junction, so there are three junctions between CE, CB, and EB. If you put that voltage beyond this voltage, then you will damage your transistor. Okay, so there is this reverse voltage of, for example, it's written here as VCO. VCO means basically is the voltage across CE with B open. So if B is you have no current in B, B is open, and you have across a CE a voltage which is your VCC beyond than 40 volt, then you will damage. This is the maximum value. You could only put VCC, voltage across the collector. Voltage supplied to the collector loop, maximum of 40 volt. And then we have VCB. So VCB is basically the voltage across a CB. So in between the collector and the base, we have 60 volt. And then VEB. So VEB, it is at 6 volt. Okay. And then the next thing that we would like to look at is also the maximum current. So it's the voltage that you could put. Now the maximum current that can circulate in the collector loop. So IC over here represent the maximum collector current, and here, for example, in this collector current in continuous, if you have a continuous current, the maximum value that it can circulate is basically 200 milliamps. So it was rated for 100 milliamp or 0.1 amp, but it could circulate a maximum of 0.2 amps or 200 milliamps. And then we have a PD. This is also important to look at. This belongs to the characteristic of thermal. It's thermal characteristic of a transistor. Because why is it important to look at thermal characteristic of transistor? Because basically the PNP junction or PN junction its behavior can be influenced by temperature. In general, what happens is as the temperature rise, the performance of the junction will be diminished or will be decreasing. So it is due to at molecular level, basically when you have more thermal energy, what happens is there will be more vibration intermolecular. So the operating or the functioning of this PNP junction will be altered, and they will be basically decrease in performance. So PD is the maximum power at ambient temperature. So it is the power that can be managed by the transistor at its ambient temperature. So here it was rated done for 25 degree. And then at the bottom over here, we have what we call as the rating factor. So what is the rating factor? The rating factor actually means that the power rating that can be managed by the transistor will be reduced by a certain rate if the temperature is increased. So here basically it says that we have the rating factor of 5 milliwatt per degree Celsius. So it means that beyond 25 degrees Celsius, for example, if you are now at 25 degrees Celsius and the temperature of operation of your application is beyond 25 degrees Celsius, each increment of 1 degree Celsius will basically reduce the power, the maximum power, by 5 milliwatt. So by 5 milliwatt. So it means if you increase 1 degree, then the power rating will not be as mentioned in the datasheet anymore. It will be diminished by 5 milliwatt per degree Celsius. So it is very important to basically manage the thermal behavior of the transistor, of the application in which you install your transistor. That's why usually when you look at the real transistor, you might have a transistor of different shape. They are basically attached to heat sink. So heat sink is the component that basically used to diffuse the heat into convection into the ambient air to reduce the temperature, to make the heat transfer as efficient as possible, so that the transistor, your PNP junction, will not be at high temperature. The next thing in the datasheet that is important to look at, it is basically the most important. After you know that you are in the limitation of under the maximum voltage and under the maximum current and at the correct operating temperature, now we are going to be interested in the real application of this a transistor, which is basically to produce a certain current gain. Okay, so in current gain, you have to look into on characteristic, and we have the characteristic of HFE, H. So usually it is written as H. H is basically a beta. Datasheet usually use the symbol H, and the value that is given for beta or H is over here. It's given in terms of minimum value, because the value could be varying in from one component to the other, but we have a range of minimum and maximum. So here we have minimum. It's important to look at minimum. Why? Because we want to make sure that we have at least that kind of amplification, that kind of we have at least the minimum this value of beta, but we could have maximum value of for example here 300. So for different, as we know, if you look at the characteristic graph of IC versus VCE, I think you remember the characteristic graph of IC versus VCE. So we have VCE, we have IC over here and VCE over here. So the graph is basically something that looks like this. So the operating area that I want to be in is this operating area here, where we is in linear area, where we have a constant beta, and this different line basically is representing different beta for different IB. So for example, this is for IB1, this is for IB2, this is for IB3, and we have a different value of beta for each for transistor that operated at each different base current. So here in the datasheet, what we will be looking at is basically it gives us the minimum beta if we have different IC and different VCE as a different operating point. So at VCE equals to 1 volt, you and at IC equals to this value, you would have this minimum coefficient of beta. Now we are going to look at the biasing of transistor. Or as I mentioned just now, biasing means basically setting the base current in order to operate the machine in linear mode. So what we call as here, we will look at the first one, we look at the base bias, and we'll have a look at the load line of base bias. So load line, what is load line, we'll see later. It is we will explain here what is load line. Load line representing the possible operating point that you might have for your transistor when you have it in so we're going to discuss the load line over here when we have our transistor bias in base, on the base. So what do we mean by bias on the base? Bias on the base means we have this kind of configuration where we have a resistor that is put on the base junction of the BJT. So we have RB over here. When you have RB over here, RB, RC, and nothing on the emitter junction, when we have RB over here, this is what we call as having a base bias. So on the collector characteristic graph of a BJT, IC versus VCE is like this graph, IC versus VCE. Load line is basically a line that we can draw. So this is the line that we can draw representing all IC versus VCE possible values for every possible IV values. So we are controlling the IB. So of course here we are controlling either by controlling the voltage or the resistor. So let's imagine that the voltage over here VBB is constant. So by changing the value of RB, we will be able to change the value of IB, right? So by changing the value of IB, we know by calculation that IC will change, therefore VCE will change. So if we change the value of RB, we will change the value of IB, and by consequence, we will change the value of IC and VCE. So this graph of IC and VCE is the graph representing basically the pair of IC of VCE on the transistor that is possible to have. So we will have different IC and VCE depending on IB, and that value of IC VCE will be represented in this line over here. So at each point of the line, you could trace basically the VCE and IC, and this is the line when you are changing the value of your RB. So how do we find this load line? That's what interests us. If we have the IC versus VCE curve, how do we find this load line in order to identify all the possible pair of IC and VCE? So example, for the circuit shown here, if we fix the base current by fixing, for instance, RB equals to 1 mega ohm, so now it's by varying the resistance RB, right? So we put RB equals to 1 mega ohm. If you do the calculation, so I'll let you do the calculation. The calculation is basically you do the KVL over here, VBB minus VRB minus VBE equals to 0. VBE here across the junction, BE is 0.7, you know it. So you would find a certain IB, and when you find IB, it should be equals to 14.3 microamps. Okay, 14.3 microamps. So let's say that if we have a beta equals to 100, if we have a beta equals to 100 for this characteristic of transistor, imagine for IB equal to this value, it gives us beta equals to 100. Therefore, you could calculate IC. IC is 100 multiplied by IB. So from IB of 14.3 microamps, you will end up with IC equals to 1.43 milliamps. So therefore, the collector current is now 1.43 milliamps. So you can calculate now the output voltage of VCE by calculating the KVL inside here. So KVL inside here is written over here, VCE. So VCE equals to VCC minus ICRC. So it is 15 volt minus, so IC that have been calculated previously here equals to 14.3 milliamps multiplied by the resistor RC 3 kilo ohm. So we get the output voltage of VCE equals to 10.7 volts. Okay, so the pair of VCE and IC over here, 1.43 milliamps and 10.7 volts. So the pair we call it is point Q. The operating point Q, IC VCE of 1.43 milliamps and 10.7 here. I'm sorry, here it's not 107, it's 10.7 volt. Is what we call as the static operating point Q. So if you have your IB equals to 14.3, which means that you have RB equals to 1 milliohm, you will have your transistor operating at 1.43 milliamps and 10.7 volt of IC and VCE. So where is it in this graph? So for example, VCE, we could say that it is probably around, so around over here, VCE equals to 10.7, and then IC equals to 1.43 milliamps. So this is milliamp, 1.43 milliamps probably over here. IC 1.43 milliamps. So the operating point is basically over here. Our point Q is over here. So if you have your RB equals to this value of 1 mega ohm, if your RB equals to 1 mega ohm, that will result in your transistor operating at this particular point. Okay, so it's operating at this particular point. But of course, what would happen is that we can change the current of IB. This current IB, we could change it by changing the resistor RB. So for different current of IB, due to the variation of RB, we may draw a line, what we call as load line, from the equation. So using the same equation, we know that here the equation over here, VCE equals to VCC minus ICRC. If we change IC, so IC we know is VCC minus VCE over RC. If we know that IC will be depending on IB and IB will be depending on therefore RB, we could write a line following this equation, IC equals to VCC minus VCE over RC. So our VCC is 15 volt. Our VCE, well, VCE will be depending on this equation over here, divided by 3 volts. So in function of VCE, we can write the equation of IC equals an equation in function of VCE. And the equation is this equation over here. So this equation basically is the equation of this line over here as what we call as load line. So what this line represents is basically as VCE change, due to, so how does VCE change? As VCE change due to the change of IC, which is due to the change of RB, IB and RB. The position of operating point of a transistor can move along this line. So this is the line that we mentioned just now with the equation of IC equals VCC minus VCE over RC. So the variable here in x-axis is VCE, which as we mentioned just now depends on IC. Depends on IC, therefore depends on IB and RB. So what is explained by this line is basically what is explained by this line is basically the variation of this operating point as the base current changes. Okay, so we have two extreme point on this dot line. The first one is what we call as saturation points, this point over here where we have maximum IC and minimum VCE, and this point over here is what we call as cutoff point where we have maximum VCE but zero IC. So let's discuss about saturation point first. So what is saturation point over here? Saturation point here is when you have maximum IC and zero VCE. So how do we have zero VCE? We would have zero VCE if we look into the equation that we have in the previous slide. We would have zero VCE if our base resistance is too small. So if our base resistance is too small, then the base current will be too large. So if the base current will be too large, then the collector current will be at its maximum. So here is basically the collector current at its maximum value. Okay, at its maximum value, of course, for the given VCC and VBB. So IC will become maximum, the largest value possible, and then VCE will drop to its zero value, drops to zero, where you would have basically a zero voltage. So in output VCE, you will have 0 volts. So if you have too large IC, which means you have an IB that is too large, you will have an output voltage that is 0. So if you are in base bias where the resistor is in your base, if the resistor is too small, then the base current will be too large, the collector current therefore will be too large, and the output voltage will be 0. So we don't want to be in this case, so where basically in this case we cannot have any output voltage. So it is basically, in terms of equivalent electrical circuit, it is equivalent to shorting between the collector and emitter. So it is as if you don't have any transistor anymore. It's like you are shorting between collector and emitter. So you have your current circulating only directly inside the collector loop, and there is no voltage across over here. Okay, so and then the second point is what we call as cutoff point. So this is the second basically extreme point or extreme condition, where you have basically it is the other way around, it's the opposite of saturation point. In saturation point is when you have the resistance is too small, but here when you have your resistance is too large. So when you have your resistance too large, resistance at the base as too large, so what will happen is that the current will be too small, and if the current will be too small, then the current in that is pulled out of the collector will be also too small. So it is too small so that it is close to 0, so it could be 0 where you don't have any current circulating. So it is an equivalent in electrical point of view. It's just like an open circuit, so there will be no current circulating. It's like an open circuit. So when you have your resistor too large, your base current will become too small. When your base current will become too small, then multiply by beta, your collector current also too small. And when you have your collector current is too small, then you will have no current circulating inside this loop anymore, and you have your VCE. Therefore, if you measure the voltage across over here, it is equals to the voltage across the VCC, or voltage supplied to the collector loop, right? So the voltage over here, there is no current circulating, so there's no voltage across RC. So the voltage over here is the voltage between this point, which is also this point, because there's no current circulating. It is as if there is no resistance. So the voltage is also equals to the supply voltage of VCC. It is open equals to VCC. So that was what we have seen just now is biasing the transistor or the BJT by base bias, putting a resistor in the base. What we could do also, instead of putting the resistor on the base, instead of putting it over there, we could adjust the base current or using the transistor by putting our resistor or adjusting our resistor on the emitter junction, on the emitter. So this is what we call as emitter bias. So it has a certain advantages that we don't have in we wouldn't have in base bias just now, where we could fall into the condition of saturation and cutoff point. So again, biasing, what does it mean? It means setting the base current so that the transistor operate in linear mode. So in an amplifier, we need that in an amplifier circuit of higher power, we need an operating point Q. So now you know that operating Q is basically the pair of IC and VCE. We need operating point Q that is immune to the change in current variation. Okay, so if there is any changes in terms of the base current, if there is any changes in terms of the base current, we need to have more or less a stable position of point Q, or the pair of IC and VCE. So in order to do so, this bias emitter, this emitter bias configuration is very useful, because the point Q will not vary on the load line. So you do not have as we mentioned just now, the load line where the point Q could vary along the lines, right? But in this emitter bias, we'll see that that will not be the case. So in order to illustrate that, let's have a look at an example. In this example, we're going to analyze this particular circuit. So in emitter bias BJT, we have our resistor in the emitter terminal or emitter junction, and then there's no resistor in the base junction. So first, let's try to evaluate the emitter to ground voltage VE. So VE is the voltage between point E, the emitter, and the ground. So it's the voltage across the resistor RE. So if you want to find VE, VE is as we look into the base loop, we could deduce VE in the base loop. So in the base loop, we will have VE, we will have VBB, and we have VBE. So if you write your KVL, you'll find that VE will be equals to the VBB 5 volts minus VBE. So by now you know VBE will take it equals to 0.7. So we will have that our VE, the voltage across the resistor RE, equals to 4.3 volts. So from that VE, what we can deduce is we can deduce the emitter current IE. So how do we deduce the emitter current IE? To deduce the emitter current IE, we know VE, we know RE. Therefore, you just use your Ohm law. VE divided by RE, you will get IE. So here IE equals to 4.3 volt that was found previously, divided by the resistor RE, which is 2.2 kilo ohm. You will get the answer of IE equals to 1.95 milliamp. So the currents that going through this resistor of RE in the emitter is equals to 1.95 milliamps. So therefore, what we can deduce is that we know that the current of IE will be very close to the current of IC, because current of IB is very, very small. When we consider that, we could say that IC equals to IE, therefore IC also equals to 1.95 milliamps. So therefore, the collector voltage VC, if you want to find VC, so what is VC? VC is basically the voltage between the point collector C and the in comparison to the ground. So for example, is the voltage in this particular loop over here, if I may draw to help you. So VC is this voltage over here, VE was this here. So VC is the voltage when you compare from this point and the ground. So if you put your voltmeter, this is what we call as VC. So in order to calculate VC, you can calculate it in this loop over here. So you have in your KVL over here, you have VC. If I redraw the KVL, you'd have VC, and then you would have so the VRC, and then finally you will have your voltage supply of VCC. So the current is circulating in this direction. So your voltage across the resistor RC VRC is in the opposite direction. So you have your KVL. If you want to write your KVL, you have it over here. VC minus VRC minus VCC equals to 0. So that lead us to VC equals to 15 volts minus VRC. So 15 volts is the VCC minus VRC. VRC is the current that I found previously, 1.95 multiplied by 1 kilo ohm, which is the resistor of the collector. So we will get VC, the voltage at this point in comparison to the ground, equals to 13.1 volts. So as usual, what we want to have at the end is the output VCE. So VCE is the voltage difference between VC and VE. So it's a comparison of different potential between point C and point E. Therefore, if you take VC that was calculated previously, which is equal to 13.1 volts, and VE calculated here equals to 4.3, you'll get VCE equals to 8.8 volts, right? So the pair of IC and VCE, so IC was 1.95, VCE is 8.8 volts. So this pair of operating point Q, 1.95 milliamps and 8.8 volt, is the operating point when we have this circuit in emitter bias. So what you can remark over here is that we have never there has never been it wasn't necessary to find the base current IB, right? As we can see, we don't depend on the base current IB. There's none in the calculation where we need to find the current IB. The calculation in the loop base is just helping us in finding basically IE. Therefore, what we can conclude is that in this emitter bias transistor configuration, we are independent of the base current, therefore independent of the beta or coefficient of a current gain, right? So regardless the value of the current IB and regardless of the current gain beta, we would have the same operating point of IC VCE. So this is what we call as a configuration. Emitter bias is what we call as beta independent. So regardless the value of beta, you could calculate the operating point, and then therefore regardless of the value of IB, you will always be operating in this operating point. So there is no variation of IB. There will be no variation of IB. Therefore, your operating point will be always at the same point, and you will not be. There is no possibility of moving on the load line as what we have in base bias just now. So this is proved by the process of analyzing the circuit that we are beta independent. So again, if I have to summarize the process of basically finding VCE over here, the first one is to get the emitter voltage. In emitter bias, we have to find the emitter voltage using the base loop, but here there is no current base at all, base current that was used, and then we have to calculate the emitter current. Once you have find VE, calculate the emitter current. Thirdly, once you have the emitter current, we say the emitter current equals to collector current, which is true in a BJT. And then finally, you calculate VC and VE. So you deduct VC from VE to get the output voltage of VCE. And then there is the other method, another method of biasing a transistor, which we call as voltage divider bias. So what is voltage divider bias? Voltage divider bias is basically the most widely used biasing circuit for BJT. It is basically, if we will look at it shortly, the analysis of it. It is basically an emitter bias with a control VBB, right? So we know that previously, if you look at the previous circuit, we would have VBB and RE, but VBB was constant. But now, in order to change the value of current of IE, what we could do is basically by changing the value of the voltage supply VBB. Okay, so how do we change the value of voltage supply VBB? It is by basically integrating a voltage divider. So if we change, for example, using a potentiometer, if we change the ratio of the voltage divider, we would change therefore a VBB inside our circuit. So let's try to analyze it. let's try to analyze it. So this is the circuit of we will call it in short voltage divider bias as VDB. So this is an example of VDB where you have basically in the input for the base, in the base loop for the base current, you have basically so this is the the voltage into the bias is the same as the VCC, so it's connected to the same power supply over here. Um, have VCC, and then which is also VBB over here. So and then it's connected to two resistor, and then there is a point tap in the middle of the resistor to go into a transistor. So if you recognize enough, basically this is a voltage divider. Okay, this is a voltage divider made of two resistors R1 and R2. There is a condition to design well your VDB. In order to well design your VDB, usually the current in the base should be much smaller. The base current should be much smaller than the voltage divider current. So the base current over here that goes into the current that goes into your junction, the base of your BJT need to be much smaller in comparison to the current that goes through your resistor. Okay, so in order to do that, basically you have to calculate the value of resistor. The resistor has to be sufficiently small so that the current goes mostly into this resistor instead of going into the base loop. Okay, so if this condition is applied where we have the base current much smaller than the current inside the voltage divider, we could consider that base current negligible. So it need to be as small as possible in comparison to IR2, IR1 and IR2 current through the voltage divider, so that it could be considered negligible. So if you are considering it the negligible, then the base circuit can be simplified into this circuit, right? So we have IB negligible, so it is as if there were no current at all inside the base, so it is as if it was an open circuit. So electrically it's the same as this circuit where you have your voltage divider, and then the base is basically not connected to the voltage divider. So what happened here? Let's analyze. So the base voltage is the voltage divider output. So there is no current, but there is a voltage, mind you. So of course there is no current, there is no current circulating, but if you tap a measurement in this point, you still have a voltage where the voltage is basically VBB. Okay, what is the base voltage over here? The base voltage that is connected to the base. So the base voltage is basically the voltage output of the voltage divider. So you know how to calculate the voltage divider, right? So the voltage output VBB of the voltage divider is basically VCC multiplied by the ratio. So the output resistor is R2 divided by the sum of resistor. So it is VCC multiplied by R2 divided by R1 plus R2. So that's what we have over here. VBB, the voltage that's connected to the base, where there are no current circulating inside the transistor. VBB equals to R2 over the sum of resistor R1 plus R2 multiplied by the input voltage VCC. So from that calculation, the circuit can be simplified. So instead of having the voltage divider, we have now VBB, where VBB is the output of this voltage divider. And then all the calculation from there, as we can see over here, this circuit is basically the same circuit as in the previous slide. It is the circuit of an emitter bias configuration. So it is an emitter bias configuration. It's just that VBB is controlled by the ratio of voltage divider. So in order to get more or less a current in IE, as in the calculation in previous slide, we could adjust VBB by modifying the ratio of the voltage divider, control the output. Okay, so the calculation from there is as in the previous slide. So we get VBB over here. In previous slide, VBB is given, but VBB here now is depending on the ratio of the voltage divider. Therefore, you can control it by controlling the voltage divider. So VE, if you want to calculate VE is VBB minus VBE. VBA we know it is equals to 0.7, and VBB it is given in this ratio over here, in this calculation of ratio. Therefore, from VE you can calculate IE, which is by Ohm law VE over RE, and we consider that IC is more or less equals to IE. So we have IC. When you have IC, you can calculate VC in the loop of the collector. And when you have VC and VE, you can deduct VE from VC to get VCE, the output voltage. So it is the same calculation as in emitter bias previously. It's just that now your VBB is controlled, therefore your IE and IC is controlled. It is controlled through controlling the ratio of the voltage divider. So that's all on biasing of a BJT in order to control the base current or emitter current. So we have seen in this week, we have seen basically in first place the reading of the data sheet. So now you know in the data sheet what you need to look at, the most important figures that you need to refer to. And then we have looked into biasing, two type of biasing. So base bias and emitter bias. So in base bias, we are basically sensitive towards the variation of IB. So we can be placed anywhere inside what we call as just now as load line. In order to avoid that, what we can do is to use our transistor in what we call as emitter bias. And to have more control and emitter bias, what we can use is the VDB or voltage divider bias. So we have finished our topic on BJT, and next week inshallah we will look into another type of transistor, which is a MOSFET transistor. So until next week, see you next week. Goodbye and thank you.